of renaming. If we're looking at function f and function g, and oh, hey, g is the function of f. In almost all cases, we at that point, at that moment, are going to say, good, we're not calling that g anymore, we're going to call it f inverse of x. Could you flip that around also? If you determine that f and g are inverses to each other, could I switch f and call that g inverse of x? I don't see any reason why not, okay? So understand that once we've made that, we've established that, yes, this is the inverse to that, there's often going to be the act of renaming one of those. Because we want to show, don't we agree that if you see f of x and it's written next to f inverse of x, we know that those are linked together now, don't we? Right? If you see f of x and you see g of x, I don't know, maybe. We've got to go run the test. But once we've tested it, established, verified it, that's when we want to make certain that moving forward, we know that these two are paired. So again, there will often be a situation to where we rename. All right? So if you're wondering, like, what happened to the g of x, all of a sudden f of x, or f inverse, sorry, of x just popped up out of nowhere, it's because we've established that it worked. Okay? So again, under these conditions, the function g is the inverse function of function f. The function g is going to be denoted by, the way we read this, is f inverse, not f to the negative first power or anything like that. All right? So two functions, f of x and g of x, are inverses if and only if both of these are happening. F of g of x equals x and g of f of x equals x. All right? Both of those have to be true. All right, so let's go ahead and tackle this first one. We are given f of x, we're given g of x. The instructions are asking us to let them be the functions below and determine if they are inverses. So the first thing that we need to do is figure out what is f of g of x. All right, so that means I'm going to plug the maroon one in for the green one, right? I'm putting g into f. So I know that function f is 2 times x minus 3. But in place for the x, I'm putting all of function g, which is 1/2 x plus 3/2. All right, guys, I'm going to pause here just for a moment. Probably slow playing this more than I need to, but is this making sense based on yesterday's stuff, how the composition is going to work here? We understand what we're putting in for what? All right, now what's my target? In order for us to say, yep, got it, inverses, what am I looking for? Very specifically, this should clean up to be what? Positive 1x. Good. All right, let's see if we get it. So when I distribute, 2 times 1/2 x is going to just be 1x. 2 times 3/2 is going to be 3. And I still have the minus 3. The 3 and the negative 3 will subtract out. And congratulations, we did it. F of g of x is equal to x. That was the target that we were hoping for. But guys, we're only halfway there. Okay? We've got to show that it works the other way as well. Now we're going to find g of f of x. So function g, as you could see, was 1/2 x plus 3/2. But I'm putting the green into the maroon, so f of x being plugged in its place now, so the 2x minus 3 goes in place. Just like we did before now, we're going to clean this up and attempt to establish that this equals x. Let's see if we get it. 1/2 times 2x is just 1x. 1/2 times negative 3 is negative 3/2 plus 3/2. They're going to subtract out, and again, we got it. G of f of x is equal to x. We got it, so what does that mean? That means that f of x and g of x are, in fact, inverses. So determine if they're inverses, yes. I'd probably write this up a little bit fancier, but I'm going to try to save a little bit of time here. But yeah, they're inverses. G of x is the inverse to f of x. All right. Another way that you may see this question is you might be given one. You're given f of x equals 7x plus 4. And then we want to figure out, okay, you're given two more, g of x, h of x. Which one of these is the inverse? Which one? So all we're going to do is let's go ahead and figure out. Let's try f of g of x. All right, so let's try this one first. So I'm going to take function f, which is 7x plus 4. And I'm going to put g in its place, so the x minus 4 over 7. So when I multiply, these 7s will cancel, and I'm left with x minus 4 plus 4, which of course those 4s are going to cancel, and we did it, we got x. So that does mean that absolutely yes, g of x is the inverse. Got that. All right. Now, maybe they both are. Maybe h of x is as well. So let's try f of h of x. Let's give this a whirl. All right. So same story. We're looking at 7x plus 4. We're putting h into the function f, so x minus 7 over 4. When I distribute the 7 through or multiply the 7 through, we're going to end up with 7x minus 49 over 4 plus 4. I'm going to rewrite this 4 over here as 16 over 4 to get my common denominators. I'm looking at 7x. Is that going to be minus 33 over 4? Any luck? Is this equal to x? No, it's not. So, not the inverse. Like that. All right, so guys, are we feeling pretty confident? Given two functions, I could determine whether or not they're inverses to one another. Now, I probably should have gone one more step and plugged it back in the other way just to really verify. But like I said, I'm trying to move quickly through this. I feel like we get the compositions. We're just trying to show you what that's all about. All right, so by my estimation, guys, and there's a little wiggle room here, admittedly, even before I get into this, but there are 3 ways to find inverses. We've talked about how you could swap ordered pairs, like we did in the table a few slides back. Now, the only downside is you have to know all the ordered pairs in order to swap them. But quite literally, what that means is that if you have, I don't know, if you've got 2 comma negative 5 on the function, that you will have negative 5 comma 2 on the inverse. That's what we mean by swapping the ordered pairs. Again, simple to do so long as you have the ordered pairs. Like we had in the table, that's all that we did was we just traded the x and the y's. So a little bit more to come on that. Graphing, we've got some things to talk about, but technically you're going to be reflecting over the linear identity. You're going to be reflecting over the line y equals x. What I would highly encourage you to do is kind of blend those first two together and kind of mesh them in. So if we are looking at the graph, yeah, I'm going to reflect over that line, but won't it be easier for me to pick out specific points and swap them so now I know where I'm going? But at the end, I've got to notice, yeah, hey, this is in fact a reflection, so this is in fact an inverse. Then the last one, solve algebraically, which, as I said at the start, I'm pretty hopeful that that's going to look familiar once we see it. Okay. If you're super bored one of these days, again, can't sleep this weekend, just go back and read through this. This tells you verbatim, word for word, like what you should do. Let's go ahead and actually do it. Like I said, I'd be happy to read this to you, but I don't think anybody wants to hear that. Again, I think that the action is going to make a lot more sense. Plus, it's going to be sort of familiar. So the graph of an inverse function. Let me use, like I said, on my screen, it's a little bit easier to tell, but still not perfect by any means. So right here, this is the function, okay? So this is my actual function, f of x. That's it. So what we're noticing is that the inverse to this function will be reflected over the line y equals x. Remember the identity, y equals x, through the origin, slope is positive 1, but it's a linear function. Okay, the other thing, very generically here, we would say that any point that lives on that function, f of x, any point, we're just generically going to call it AB. So now we know immediately that the point BA is going to be reflected on the inverse. Okay, is this stuff sounding familiar? Did you guys talk about the graphs of inverse last year? I think that was maybe a teacher by teacher thing. The Algebra 2 teachers that I spoke to, some were like, yeah, we definitely talked about that. And then others were like, I may have mentioned it, but we were really more focused on this or that, which is fine. Like I said, you do what you do in Algebra 2, we'll take the rest, and we'll go further here. But like I said, I also don't want to be overly redundant and talk about it for 5 minutes when you guys are like, yeah, we get it. I got that last year, that sort of thing. All right? So again, if the point AB lies on the graph of f, then the point BA is going to lie on the graph of f inverse. Vice versa, we can flip-flop back and forth. So the graph f inverse, it is a reflection of that line y equals x. So if we wanted to sketch the inverse, all right, a couple of different ways or a few different ways that we could approach this, realizing that I am attempting to reflect over that line right there. Like I said, we could take that parabola and attempt or try to just reflect the whole thing all at once, but that's going to be kind of tricky. So let's start with the easiest possible points. Any point that's on the line of reflection, yeah, that's going to stay put. It's going to stay exactly where it is. So we know that on my function, we clearly have points. Well, on my inverse, I'm going to have points in the exact same spot. Okay? So I'm also noticing that we have, I was going to use a different color. Let me redo that. So on the function, we have a point at 2, 0. When I swap the x's and the y's, where does that put my point on the inverse? 2, 0 becomes what? It becomes 0, 2. Okay? Looks like on my function, looks like we have a point right there at 3, 1. So 3, 1, what does that become on my inverse? It becomes 1, 3. Looks like on my function, we've got a point up there at 0, 4. Swapping the x's and the y's, what does 0, 4 become? 4, 0. All right, what do you guys think? Do we have enough red dots to make an accurate parabola? What if your answer, seriously, I mean, I roll my eyes at it, but I do it secretly. I wouldn't do it in front of your face. But what if you were like, no, I don't see it. I don't see it. Could you keep on going? Could you keep on finding more and more points? Absolutely, absolutely. But I think that we have plenty. So looking something like that. There we are. All right, now this next one's going to be a little bit trickier because I'm going to use some, some tactics here, if you will, because it doesn't go perfectly through as many points. For the relative min and relative max points, they're not perfectly exactly. So we're going to, like I said, we're going to make it work, though. All right, let me get this sketched in. All right, so there's my line of reflection. This is what we're supposed to be sketching over. All right, as we said before, great place to start is with the knowledge that any of these points that are on the line of reflection, they are going to stay put. Okay, it appears on my function that we have a coordinate right there at -2, 0. So -2, 0, what does that become? -2, 0 becomes 0, -2. Good. All right, now we're going to, like I said, approximate here. I don't know, we could call this, it's probably up for debate, but I would say that relative maximum point, I don't know why let's zoom in on this so we can really see it. That relative maximum point, I don't know, about -1.2, 2.1, maybe? -1.2, 2.1. Like I said, at least we're in the vicinity. Nobody, namely myself, is claiming that that's exactly precisely where it's going to be. But if that's what we're going with, where's the inverse point going to be? 2.1, -1.2. All right. What about this relative minimum point? Oh, let's not make it harder than it needs to be. It's probably not exact, but what are we thinking? Like 1/2, -1/2? At least we're in the vicinity, correct? Okay, it's probably not exact, but hey, I'm not telling anybody if you aren't. So once we swap these, where are we going to build that piece of the graph? -1/2, +1/2. All right, what do we think as I zoom out just a little bit? Is there enough here for me to make my sketch? And if honestly, if your answer is no, let's figure out that point. 1.5, 3. Where's 1.5, 3 going to go? 1.5, 3 becomes 3, 1.5. So like I said, if we needed another point, there it is. Like again, we've got this. I think that we have plenty to make that sketch. All right. How are we doing here, guys? Hanging in there? Making sense? We've got this. So again, blending those two ideas together, yeah, it's just a reflection over the line, but let's be honest, that's kind of hard to do, okay? So yeah, it's a reflection over the line, but you're going to get there a heck of a lot simpler by taking your coordinates and swapping the x terms and the y terms. Realizing all along that there's way more to the story than that. We're really actually trading the domain and the range values, okay? All right, next up, the idea of one-to-one. There's a lot of words here, so we'll try to paraphrase. But the first part is going to be fairly important here. So we say that the reflective property of the graphs of inverse functions gives you a geometric test for determining whether a function has an inverse function. All right. We call it the horizontal line test, right? Now, Did you talk horizontal line test last year in Algebra 2? I was assuming no, but like I said, I was going to be speaking here the next minute or two as if, hey, this is stuff you've never heard of, but I also feel like that would have been a waste to talk about that in that setting. So let's go back, rewind. What did the vertical line test determine? Whether or not your graph was a function. You're looking at this graph, if it passes the vertical line test, hooray, it's a function. Got it. Now, do we agree that as I'm flipping the x and the y terms, that really what's happening is I'm taking my graph and I'm flipping it on its side, basically? So now what we're saying is, what is going to happen to this graph? I'm looking at the original, I'm looking at the function. What's going to happen to that graph after I invert it? Once I invert it, is it then going to be a function? So like, for instance, this first one, the parabola, that parabola, sure, that passed the vertical line test. That was a function to start. But I inverted this thing. Its inverse was not a function, was it? That's a problem, right? In some settings. So this would be a situation where, no, that's not the word that we use. It's not invertible. So you're going to be asked, is this invertible? So what we can do is, and I'm not wanting to erase it right now, but we could look at that original function, and yeah, it passes the vertical line test, but wouldn't the horizontal line test, remember in the spirit of just switching x's and y's, wouldn't the horizontal line test tell us whether or not the inverse is going to pass the vertical line test? You guys with me on what I'm trying to say there? It's a shortcut, people. That's all that it is. Hey, I want to know if this, my original function, I'm looking at its graph right now. I can determine, yeah, it is a function. I want to determine if its inverse is going to be a function, but I don't really want to draw the whole thing out. I don't want to draw in my line and swap all the points and do it. Isn't there a shorter, faster? Yeah, the horizontal line test is going to tell us. Does that make sense? When you pass both the horizontal and the vertical line test, your function is said to be 1-to-1. Okay? For every input, there's one output. But that only happens, like I said, when you pass both horizontal and vertical line tests. All right? So again, that horizontal line test, it's the same as the vertical line test in the sense that you can draw a horizontal line through that does not intersect in more than one location. That's what we're talking about. So a function is 1-to-1 when each value of the dependent variable corresponds to exactly one value of the independent variable. So you've got one x that's going to match to one y. Okay? A function f has an inverse function if and only if it is 1-to-1. So again, your function has to pass both horizontal and vertical line tests in order to be this 1-to-1. All right? In order to be and then it works the other way. In order to be 1-to-1, it had to have been, or in order to have an inverse, it had to have been 1-to-1. All right? So a couple more things here. We want to use the horizontal line test to determine whether or not the function is invertible. That's just a fancy word for it doesn't have an inverse. So what do we think here? F of x equals quantity x minus 1 cubed plus 2. First off, is that a function? I'm asking about vertical line test right now. Is that a function? You bet. Does it have an inverse? Passes the horizontal line test, so you bet it does. Okay, so this was just a yes/no question. Yes, has an inverse. Yes, it's invertible. All right, now last thing we want to talk about today, I would have felt better if I had maybe like 2 more minutes, but this I'm pretty confident that you're going to remember how this goes. So we've talked about here's a function, here's another function. Are they inverses, or is this the inverse of that? And there was some algebra that we could do along the way. What we're talking about now is here's one function. It's on you. You go find the inverse. That's different now, right? It's just an algebraic thing. Remember, we're still in that spirit, that concept of swapping x's and y's. That's all that we're really trying to do. So the way that we're going to find an inverse algebraically, the first thing that we need to do, because we've gotten into f of x notation, right? First thing we have to do is recognize, well, that's just y. So I'm going to rewrite this as y equals the negative 4x minus 9. That's the first thing we need to do. Then the next thing is literally we're going to switch all x's and y's. So anywhere that I see a y, I write an x. Anywhere that I see an x, I write a y. So does everybody understand that move that we just made? This just became x equals negative 4y minus 9. Then my next move is I'm going to solve for y. I'm just going to do the algebra to get y isolated all by itself. So I'm going to add the 9 over. That was an add. So now I've got x plus 9 equals negative 4y. I'm then going to divide both sides by negative 4. And we've done it. We got y, bless you, is equal to x plus 9 over negative 4. Now the last move is we're going to replace the y with f inverse of x. So f inverse of x. Now, if you're a paranoid person, and you're like, gosh, I don't know, did I do that right? How could you test if you did it right? I could take this inverse function and plug it into the original function and vice versa. When I do that, what should I obtain? Positive 1x. That's it, guys. That's how it goes. They may get a little tricky if you see one like this this next guy here, where you have x's in both the numerator and denominator, but I promise you do nothing differently. We're going to start by making f of x into y equals. We've got 5 minus 3x over x plus 2. That next move is, as we've said, oops, not that. I'm supposed to change x's and y. So I'm going to call that x equals 5 minus 3y over y plus 2. And I need to, basically, I don't want a fraction anymore. I'm over the fraction. Let's get rid of the fraction. So would you agree that if I multiplied the right side by y plus 2, that would clear my fraction? But I've got to do the same on the other side, don't I? So I'm going to rewrite that as x times y plus 2. That's going to be equal to just the 5 minus 3y. Did everybody see how we got there? So when I distribute on the left, that's going to become xy plus 2x equals, right side is still the 5 minus 3y. Is everybody still with me? Now here's the deal. What am I trying to solve for? What am I trying to get isolated all by itself? The x or the y? Connor, you just said it. I'm trying to get the y by itself. Wouldn't it be smart for me to get all the y's on the same side? So I'm going to move the negative 3y, I'm going to move that over. Anything that doesn't have a y, you know, like that 2x, I'm going to move that to the other side. So does everybody understand what I just did here? I added the 3y over, I subtracted the 2x over. Now I have all my y's on the left side. I have all my stuff that doesn't have a y on the right side. So what could I factor out of the left side, please? Y factors out. X plus 3 is left. I still have my negative 2x plus 5. So last move, I need to get rid of anything attached to that y. So I'm going to divide by the x plus 3. And we did it. That canceled. Y is all by itself. So y is equal to negative 2x plus 5 over x plus 3. I said last move like 3 times. The y is going to be rewritten as f inverse of x. All right, guys. Do you remember doing this last year? Maybe not. Okay, all right. Miss Kimball lies sometimes, so yeah, no, I get it. I get it. Man, I probably misunderstood her. Okay. All right, so guys, we didn't hit that last example, but I think we've got it. Homework assignments on page on page 90. The book shots, screenshots, they're available on the Google Classroom. But yeah, we'll get you going on that. Talking about these on Monday.